4.6 billion years ago, cosmic dust and ice particles around the newly formed Sun started to form larger bodies in a process we call accretion. When the rocky bodies became larger, gravitational attraction led to collisions that formed the first planetesimals. Catastrophic collisions of planetesimals formed Mars-sized planetary precursors, which eventually merged to form terrestrial planets. Soon, after the main building stage of the terrestrial planets, the planets collected planetesimals that remained from the main accretion stage. This process is called late accretion.
I'm Harry Becker, and I'm the speaker of the collaborative research program Late Accretion on the Terrestrial Planets. Well, we have these three different research areas because it's a broad topic. In research area A, we study the timing of late accretion. More specifically, this means we look at the ages of the big basin that formed on the surface of the Moon. We are looking at the question whether these basins were produced by different populations of impactors. And in general, we really want to address the impact history of the Moon since its formation and try to come up with a quantitative model for this. In research area B, we study the composition of the materials. Specifically, we are interested to study whether the late accreted material was volatile rich or volatile poor. That means whether elements like carbon, hydrogen, or sulfur were delivered late or whether they actually were delivered early during the formation history of the terrestrial planets. We do this by analysis of materials like meteorites, but also terrestrial samples, and we also do experiments to study the partitioning behavior of these elements. In research area C, we studied geodynamic processes that were relevant during the accretion history of the terrestrial planets, processes like core formation, but also giant impacts and the consequences, the heat temperature distribution within the terrestrial planets, and the exchange of the magma oceans, solid part of the Earth, and the atmosphere. In Berlin, we have as partners Freie Universität Berlin, Technische Universität Berlin, and the Research Institute at the Museum für Naturkunde in Berlin, but also the Institute of Planetary Research at the German Space Agency. At Universität-Münster, we have Institute for Planetology, the Institute for Mineralogy, and the Institute for Geophysics.
I'm Thorsten Kleine, and I'm the Deputy Speaker of the TRR. So a particular strength of our program is that we have very different skills from our partners and that these skills are complementary. And we combine expertise in geochemistry, petrology, geophysics, and planetary science. And by using these complementary skills, I think we gain significant synergy and a much better understanding of late accretion and how it is embedded into the overall planet formation process. We have weekly seminars where all partners participate. But then we also have workshops and seminars where people from both Münster and Berlin attend, just like the annual retreat or summer and winter schools. And then, most importantly, we also have projects where PIs are both in Berlin and Münster so that people naturally work together and meet on a regular basis. So for the future, I think what this program is leading us to is that we finally will understand what it takes to make a habitable solar system. So looking at these exoplanetary systems, we see that the inner solar system is much more massive and has much more massive planets, whereas our own solar system is mass deficient in the inner solar system. And that raises the question of whether this is a requirement to build a habitable planet. To address this question, to understand this, we first of all need to understand how planets in our own solar system formed and whether or not this was different from exoplanetary systems.